Hello, Professor Rana. Yes, we can start. I hand over the session to Professor Rana. He is delivering first lecture of this workshop. Professor Rana, can you please adjust your volume? Your voice is very low. Or it is low at my end. Okay.
Am I audible now?
Yes, sir. Yes, you.
Okay. Is my screen visible?
Yes, sir. Your screen is visible.
Okay. So, I don't know how many people are there in the session and what is the configuration. You are keeping an eye on the chat?
Yes, I'm keeping eye on the chat, and around 48 people are in the session. So now audience is mixed. There are college teachers, there are PhD students, there are 2-3 MSc students are in session. But I hope even of them have taken first course in linear algebra.
Good.
Yeah.
I may not assume much about linear algebra, but I will be going a bit fast on some of the topics that they may already know. And the aim of my part is quickly cover the basics of linear algebra, the standard course, namely basically vector spaces, independence, dependence, and then looking at transformations and finally coming to fundamental theorem. Yeah, please keep your mics for the time being muted. As and when you want to ask a question, please feel free to ask a question, unmute your mic and then ask a question and mute it back. Or if you put the question in your chat box possibly, then Dilpreet can refer that there is a question. I don't mind if you disturb me in my lectures. Okay, I actually, in my classroom, I appreciate students ask questions. So please feel free that your voice is heard by me and my voice is heard by you. But keep your mics switched off when not asking a question so that others are not disturbed. Okay. Okay. So this is a question I normally ask whenever I start teaching any course. This linear algebra being one of the favorites with students, and almost everybody doing mathematics has to go through it. So you will see at the here there is something called YLinear algebra. So I would like to start putting this as a question to all the participants, and some probably give you 2-3 minutes to put your ideas in the chat box, and then probably respond to that. So I am starting with a question and hoping that you'll put your ideas in the chat box. Yeah, so please go to the chat And yeah, are there any responses, Dalpreet? Hello?
There are no responses, sorry.
Nobody wants to respond to why do you study linear algebra? There is one very good obvious answer that everybody should have put it. Can you guess the obvious answer? Why do you study linear algebra? No? I think I would appreciate. I can't see the list of participants. So, can you guide me with Dilpreet from my screen?
Okay.
How do I look at some of the participants' names? How do I configure that?
Okay. So there are some students. So, you unmute yourself and answer Professor Rana if you're finding it difficult to type it one by one. Anyone who want to answer Professor Rana's question?
For solving linear system of equations.
What? Solving a system of linear equations?
Yeah, that is the one use of linear algebra.
Yeah, Ranjit said that. Anybody else would like to say something? Arup Datta, Devanshu Biswas, anybody can say anything. Why not come out? Um, yes? Who is it?
बोलो our everyday hello
Hello? Yeah, Sushmita. Right.
yes sir.
Please go ahead.
So our everyday task, our everyday life is fulfilled with linear algebra. Even the smallest task, like able to pay money in coins, like if somebody asks us to pay 100 rupees and we have several coins, 10, 20, so even that smallest task, it is based on linear algebra. It is ultimately a system of linear equations, and once we can find the solution, then it is linear algebra. So even the smallest task, and then we can go on building on that. But even the smallest task is linear algebra, which we can see in our daily life.
Okay. So, Sushmita says even the smallest task in our day-to-day life is based on linear algebra. That is a very interesting answer. I would like to explore that more. Probably interact with Sushmita later on and talk to her. What exactly she has in mind, probably she has one or two examples she would like to say. But anyway, anybody else would like to have the opportunity of saying, or shall I go ahead? No? Okay. Dilpreet,
Yes, sir.
see, when I'm sharing my slides, I can't. Earlier, I could see the grid view of
Okay.
the participants. Now I'm not able to see it. Is it because of I am in the presentation mode? That is the reason.
Yes, yes, yes. It is the reason.
So, there is no way of seeing the participants list on one side and my presentation on the other side. Simultaneously, this is not possible in WebEx.
I don't know. I don't think so.
Yeah.
Sir, it is possible. You need to just click on this participants. The
Yeah.
right hand side tab participants. If you click on this, right hand side all the participants will appear.
But I see only Vivek. I only see 2 or 3. I don't see a grid view.
No, it will not be grid view, sir. Only names will appear on the right hand side.
Yeah, names also. Only I can see your name and then two other names I can see at present. Only three names are visible. So probably I have to slide and forward, backward and see it.
So if you double click on that, all the names will appear, but then your screen will be gone. So
then I have to represent my screen, is it?
yeah. So which screen you will be able to see? Only 4. Yes.
Okay. So now my screen is visible to everybody. I'm just clarifying that I have not done messed up with the.
Yes, sir. Your screen is visible. Yes.
On the corner that I see some names like your name appearing. Is that visible to everybody?
Sir, that will be different for everyone because view will be.
Okay, no. I'm just wondering. My presentation view is not hindered by something else.
Your screen is very much visible, sir.
Fully. Okay, no problem. Then I go ahead. Okay. So let us start with my presentation. The first part is YLinear algebra. So there is a short video here. Please have a look at it. And this video showed you some in the visual format, some applications of linear algebra, meaning that all these fields use linear algebra, some in an elementary form and some in the advanced form. So, and hopefully you will see some of the applications in the later lectures which are planned. But to begin with, because many of you are teachers teaching at colleges, one should be aware of where linear algebra is used and tell students so that they are motivated to learn the topic. Higher studies in mathematics, physics, computer graphics, economics uses very heavily linear algebra. Of course, statistics finds applications of linear algebra. Electrical engineering has applications from linear algebra, heavily dependent on that. Mechanical engineering and so on. So the list is sort of very partial, very sketchy on how linear algebra sort of is used. So what is linear algebra? You can ask this question. Okay. Right. So linear algebra basically is, in my view, is study of linearity, which arises mainly from two sources. One is study of system of linear equations, and the other is study of geometry in the algebraic setup. So these two, I think, are the main reasons why how linear algebra evolves. And so it's linear, that is coming from the linear equations, and geometry in the algebraic setup gives you the algebra part of it. So that is linear algebra. So I'll try to sort of indicate how that happens. So let me just begin with the simplest thing, the linear equation in two variables. Is there anybody whose mic is on? Hello? Is there anybody whose mic is on? I can hear those sounds coming, something falling and some breaking. So I was wondering. Okay. Right. So this is the elementary thing we learn in our, I think, school, probably in the 8th or 9th standard. Mathematically, it is the set of all points in the plane x comma y, say that the relation between x and y variables is ax plus by equal to c. Right. Did I do something? Where am? Hello?
Professor Rana, your slides are not visible now.
No, I was wondering whether I logged out myself or something. So
No, you are logged because I can hear you. But
okay.
slides are not there.
But, okay. Let me just close this also so that nothing is visible. Yeah, is it okay now?
Yes, it's fine now.
Yeah, okay, fine. Thanks, Dilpreet. So at this stage, I would like to introduce a software called Geogebra. This is how many of the participants, just put in the chat box, are you aware of Geogebra? Just say yes or no. I don't know whether I can conduct an opinion poll or not. So chat box?
Few students are saying yes and few are saying no.
No, okay. So this is an open source software, and it's very easy to learn and very easy to operate. There doesn't have a much of a learning curve. So let me just show you some aspects of it. so that you are able to. Oh gosh, oh, this link is not working. Okay, I'll have to open. I thought this should open actually, but it's not working. Okay. So this is for those who don't know anything about GeoGebra. This is a software used for algebra and geometry. So this left hand side is algebra, right hand side is geometry. I don't have time to teach you all these things, so let me just write ax plus by plus c, ax plus by equal to c. Enters. Right sliders. Yes. So you see, I just entered ax plus by equal to c. It has plotted for me a equation of a line. So let me make it slightly more glamorous. Change the color to say green. Change to slightly bigger one. Right. So this is the equation of.
Sir, sorry
Yeah.
to interrupt you, sir. Actually, we are not able to see the GeoGebra screen. Your slide is visible here, but
Oh, okay. So I don't know. I think probably I have to share the full screen. I think probably, right?
yeah, there is an option of sharing only that particular screen. Maybe you have to stop sharing and then share again.
I don't know where is that control panel for Cisco there. It's not visible anywhere at all. I can't see that. Okay, probably I don't know how do I log out also.
Maybe sir, you can stop sharing and then share the GeoGebra screen.
Yeah, that is what I'm saying. Okay, meet now. Where is that? I was on the web, joined on the web.
Sir, it may be shortcut may be present in the lower bar of your laptop. The blue green. Can you see that?
On my lower thing, I can't see anything other than. Okay, let me just see what is it. Participants can now see what you are sharing.
Okay.
Expand.
Now
I
we
can
can
see the part.
mm,
Now you are
see
able to
only
see what?
black space. Not even your slides are not even visible now.
Oh, okay, no, wait. No. Now it has come. So it was hidden at the top, not at the bottom. Okay. So
Okay.
stop sharing
Yeah.
and share. What shall I share? Is there any one of the windows which says screen one? Maybe the one which shows everything probably.
Yes. Now your desktop is visible to us.
Desktop. Okay, good. I think that is what I wanted.
Okay.
Right. Okay. So your okay. This was visible. So let me go back to GeoGebra. So now GeoGebra is visible.
Yes.
Okay. So I said something. See, there is an input bar at the bottom. This is open source software available to everybody, and it's open source, so it's free and very easy to learn. So what I did, I entered at the bottom ax plus by plus c. Okay, so probably let me show you the object properties so that you are able to appreciate a bit more. Basic. So oh yeah, it's already doing it. Fine. So now You see what why this is software is interesting is this is the equation of linear equation ax plus by plus c. Ax plus by equal to c. So here the value of a is 1, b is 1, and c is 1. So I can change those values. So let me change, if I change a, so I am changing the coefficient of x. You see what is happening to the line. Okay? Its slope is changing. Okay? Because the coefficient of x. This is b, the coefficient of y. Again, that will also change the slope. Right? And what does the c does? It moves, that is the intercept form. Okay, so that is the intercept, that is the c. So it is a dynamic geometry software giving you the input about visualizing geometry in an interesting algebraic way. On the left side is algebra. So system of linear equations. Let us look at two linear equations, and which we normally do in our. So let me look at another line, y equal to mx plus c. What happened? Something else has happened. So it is y equal to mx plus c. Yeah, so that has given me another line. So here I use y equal to mx plus c form. So I change that slope is changing, and intercept is c. That c is already there, so that is changing. Okay. So this is a very good way of introducing students for geometric viewing of system of linear equations. So point of intersection is the solution, and so on. So I just wanted to introduce that you can introduce this and explore at your own pace how and when and where you should introduce this. Right. So let us, what are these points x and y? This is called, we say the points on the line represent the solution set of that equation. Okay. So given two equations, one would like to know what is the possible points which lie on both the lines. So the possibility we know is either parallel, they're coincidental, or they intersect. The possibilities. And all these things can be shown very nicely visually to students by looking at such things. And in Geogebra. So let me not go into Geogebra at present. Okay. So let us, if you want, you can give it in Geogebra. And if you do it in Geogebra, it becomes very interesting for students. Here you can see green and red lines, they are coincidental. So infinite solutions are possible. Now only one solution is possible, right? So you can ask students to find out when there is no solution possible, right? The lines will not meet, and they should realize that this will happen when they are parallel. What does parallel lines mean, and so on. So let me not go into too much into that, because this is, but this is, I'm showing it for the single purpose of those teachers who teach at college level, and when they start teaching linear algebra, visualizations help students to learn many things. Okay, so here is a beginning of what we call as the method of solving, geometric way of solving. Two lines, red and blue, they meet at a point. So how do you find that point? So the question now is, how do you locate that point? So to locate that point, one looks at what is called a combination of the two equations. So one looks at A. So first equation is A1x plus B1y plus C1. Other is C2. So take a combination of the two, linear combination, AX1 plus BY1 plus lambda times. So if a point lies on, so this line will pass through the point P, of course, the common point of intersection. Okay, because so you C1 plus lambda, but its slope will be different. Okay, so to find where is the point of intersection, if you make that line, okay, that line, this line, pass through the P in a way that it is perpendicular, right? Then the equation of the line will be, this is the x coordinate, right? So x is equal to x naught, and if it is parallel to the x-axis, that line, then the solution will be y equal to y naught. So the point coordinates will be x naught and y naught. Again, I can show it in GeoGebra, but let us do it more algebraically. Okay, so the equation x is equal to x0 gives the coordinates of the point P. Similarly, the y coordinate you can find out. This requires lambda to be equal to this. So this is how we solve system of linear equations actually. So this is what is called elimination method. So algebraically we say that the system ax plus a1x plus b1y plus c1 is same as the system a1x plus b1y plus c1 with x is equal to x0, and x0 is given by this equation. Yeah. So this is trying to solve two equations in two variables geometrically, and this is algebra behind that. So so this is called the variable elimination method. You can do it for three variables also, and let me not go too much into that because most of the people know that. But let us try to get to the core of this elimination method which we teach. Okay, so let us look at this example. So analyze the elimination method for the following example. There are three equations: x plus 3y plus 5z is equal to 0. And the second is x plus 2y plus 3 is equal to 1, and x minus z is equal to 1. Right? So I think it will be a good exercise at present that people, participants who are just listening, solve this system and try to see whether you can solve it with the knowledge that you have solving system of linear equations. In the chat box, please put your answer whether the system has a solution or not. If it has a solution, how many it has, and how did you solve that method? So whether it is a simple thing, coefficients are not very big, so you should be able to do it in 2 or 3 minutes. Dilpreet, you are looking at the chat box.
Yes, sir.
So as soon as somebody puts in a remark, please.
Okay. You.
No, sir.
Uh,
Yeah,
no answer till now.
no, still now. Good. That's it. That probably says we should go more slow, I think. You said there are some MSc students,
Yes.
so young blood should be able to solve it fast.
no solution for this system.
Pardon? Say it slowly, please.
People are saying there is no solution.
No solution.
There is no solution. Okay, good. So at least some mark is there. So let us see that. So what we do is E3 minus E1 and E2 minus E1. We get these equations. And once you do that, okay. So finally you get an equation which says 0 is equal to minus 2. Okay. So that is impossible. So the system does not have a solution. Right? Good. So let us continue this. Is absurd, so the system has no solution. And a similar thing we can do for this kind of some more examples. The basic idea is that from the first equation, we try to convert into first equation as it is and try to eliminate the variable x1 from the remaining two equations. Right? That we can do by putting the values of x1 into the second and the third, and then trying to eliminate the third. So that gives you a solution. X2 is equal to 2, x3 is equal to 2, and putting back this gives you a value of x2, and putting back gives you the value of x1. So this has a unique solution. Right. So one goes on this way, and one can write down x3 is equal to 2. So when you put the value here, you get the value of x2 in terms of x3 and value of x1 in terms of minus 2. All these things we learn in our school. So there is nothing much new probably I am telling you. Okay. And you can look at some more examples. So the question is there a way of doing, so you can have examples where there are infinite number of solutions possible. For example, if you look at only one equation in one variable, that will have infinite number of solutions, because you can put any value for x3 and any value of x2, and that will give you value for x1. And you can put infinite values for x3 or x2. Okay. So let us so the observation from these examples. So what I am trying to tell you is that when you teach these things for the first time to the students, you should make it apparent to them that there are three things that you are doing. When you are trying to eliminate variables, your equations, any two equations are possibly interchanged. An equation is multiplied by a non-zero scalar, and one equation is added to another equation. So when you do these three operations, your system changes, but the solutions don't change. That is the important thing. When you interchange these two things, okay, then nothing, just renaming the equation 1 to 2, 2 to 1 or something like that. When you're multiplying by a non-zero scalar, so linear equation equal to 0. So when if you multiply by a 0, then you're killing that information. So you should not multiply by 0. You should multiply only by a non-zero scalar. And then one equation is added to another, that we saw in the geometric way of solving it. So the solution does not change. So these three are operations on systems of linear equations which do not change the solution set. So this is the output of showing the various examples. Okay, and you should realize that the variables do not play any role in computations. The variables x, y, or z, x1, x2, xn, and such things don't play. It's the coefficients, the scalars, which are important. Okay, so that motivates one to look at what is called system of linear equations. So one formula is defines a system of linear equations. Okay, this way. Okay, so this is the first equation. So we have got m equations. The variables are x1, x2, xn. These are the variables, and so this is. So this is a collection of equations which have m equations in n variables, and we would like to find a solution. A solution means a value x1, x2, xn, so that it satisfies all of them simultaneously, right? And the method we know is that of, we define what is called a solution. Solution is a vector point in Rn such that when you put, you'll get a11 s1 plus a12 s2 b1. So all the equations are satisfied simultaneously when you replace x1 by s1, x2 by s2, and xn by sn. So that is called a solution. So the aim in system of linear equations is to find out all possible solutions of the system if they exist. And we saw examples that sometimes the solution may not exist. So find out ways of saying that the solution exists or does not exist. And if it exists, how to find all possible solutions. So the variables are x1, x2, xn. Equation coefficients are a11, a12. So you have the first equation a11 x1 plus a12 x2 and equal to b1. So these are the coefficients. So we said what matters is these coefficients, and if we keep the order intact, that a11 will be the first variable coefficient, a12 will be the second variable coefficient. So then that motivates one to define what is called a matrix of order n cross n. So this is just a collection of numbers, m times n numbers, arranged as rows, the first row, the second row, and the mth row. And each row has got columns, each row has got entries. A11 is the first one. So you can also think of columns going down. So the first column here, the second column here, the third column, nth column, right? So there are m rows, m is the first index, m rows, and n columns, n is the number of columns. Columns is going down, and saying that there is a row, you are going horizontally. So this is what is important as far as the system of linear equations are concerned. And so you define what is called aij, aijth element of that matrix. So this aij indicates it is in the ith row and it is in the jth column. So this entry is aij entry of the matrix. So all this is known to you, so I will not go into much. Okay. So you can refer, if the matrix is of order of m cross m, that means m rows and one column, then you say, so this is a row vector. Okay. And m rows and one column. So this is a column vector. Vertically down, you can call it as a column vector. Okay. So a matrix can be thought of as consisting of m rows, row 1, row 2, row m, and the columns that going vertically down. Okay. So there's a column vector, there's a row vector. I hope all of you are familiar with something called Rn. I have not defined it formally. Actually, one can spend a lot of time on what is Rn and why this object is important. But let us not go into that. And when we have a column vector, we also identify it with the point x1, x2, xn in Rn. So we'll identify points in Rn with the column vector and vice versa. Okay. So two matrices are same if their each entry aij is equal to bij if two matrices are A. Mostly we'll be concerned with entries which are real numbers or complex numbers. This collection of, because they arise for us for the time being from the field of real numbers or complex numbers, but the entries could be from any field actually, or actually you can put rings also. So we'll, as and when we come across those, we'll probably specify what are the entries. Now, for the time being, the entries will be either real numbers or complex numbers. So addition, scalar multiplication, all this transpose, all these things are known. Okay. So if at any stage you feel you don't know something, then please say I will stop matrix multiplication, matrix addition, matrix multiplication is associative, and so on. These are very elementary things. So A transpose, AB transpose is equal to B transpose, A transpose. Okay. Anybody has a question to ask at this stage? Because I'm going to change my slide. So I'm just wondering whether if anybody has a question to ask, please ask. Otherwise, I will go ahead with my presentation. Yep. I should have kept all these things ready outside, but there is a there is a slight problem. So probably I'll pick up something. So I'm using. Let me pick it from. Okay. So I think this is it visible to everybody?
Yes, sir.
Okay, okay. So this is a system of equations. So this is what we said. So I think changing the order of the equations does not matter. Multiplying one equation with another does not, with a non-zero scalar and adding to the other does not matter. So these are the operations which do not change the solution set. So these are called the elementary row operations. Okay, and finally doing these operations, your system of equations comes to this form. So it will change. Your given system will change to something. So the new change system, which is equivalent to the earlier one, will be written as C11x1 plus C12x2 and C1 and xn equal to some d1. And in the next one, the variable x1 will be eliminated, so that will start with x2 and so on. So probably it will go up to variable r, and there will be some equations at the bottom which may look like 0, 0, 0 equal to 0. Okay. So this is the kind of thing we would like to do for a general system of linear equations. So one would like to make it instead of okay. So let us. I think probably this is okay. Okay. So the system will be inconsistent. For example, let me just go back. If so, here are the 0 equal to 0, this part. So let us forget that. So let us look at the part here. Probably here in this equation, the last equation here comes out a non-zero number on the left hand side equal to 0. So probably that kind of a thing happens. So then we will say that the system is inconsistent. That is what we saw in that example, right? If not, then the system, if that is not the case, then we'll have solutions. Okay. So, so the system is consistent with n minus r variables, because in this how many variables are there? So the up to r we have come. So these are n minus r variables, which can be given arbitrary values. Okay, and then you can compute. So xn can be given and backward computation is possible. So those arbitrary values. So once that is known, you can go previously and so on. So this was actually my slide has changed. I have got around 10 minutes to probably finish today's talk, right, Dilpreet?
So this is 1.5 hour lecture, so you have around 30 minutes.
Oh, 30 minutes more. 5:30 we started. Oh, good, good.
We started at 5:30.
Okay, okay. Now, because we logged in at 5, so I was wondering what is happening. Right. So, for the system of linear equations, this is what we want to do, right? So, okay. Yeah. So, this is the system of linear equations, coefficients, and we have already made a. So, this is the form we want to. Gauss elimination method says I should be able to bring my system to this form and then make conclusions from there. So, this special form of the matrix is given a name. Now, here is something which I would like to ask the audience. We are trying to solve a system of linear equations, right? And then suddenly a new object called a matrix appears into the picture, right? And we are saying that to solve the system, we should do those three operations. One, that is interchanging any two equations is possible. Okay, so interchanging any two equations is possible. And then second was multiplying by non-singular scalar is possible. And then adding one row to one equation to another is possible. So this is the kind of thing what we're saying. So you can, in this equation, you can multiply by any non-zero scalar, that is okay. So it will change, but the solution will not change. You can interchange two equations if you want to interchange. Okay, you can call this as the first one and this as the second one if you want, or interchange first with the last one. That does not change the system. Okay, and then what you should look at is third thing, that I can add one equation to another, that also does not change. So there are three elementary operations which do not change the solution of the system. Now the question that I wanted to ask the audience is the following before I go further. What do you think? Why do you think these matrices become into linear algebra? I want to solve a system of linear equations, and suddenly Gauss elimination method says I can do these operations, and I can bring it to a special form, and that will help me to deduce whether the system has a solution or not. Right? So, where does this new notion of an object called matrix fits in? Can somebody from the audience respond to this question if you understand the question? Where does the matrix notion of matrix enter into picture? Why do we have to bring in this new notion of matrix? Yes, anybody?
Somebody replied, Sharma, she replied that to make solution.
To make
The
yes.
solution. Yeah.
Good. So at least there is a response saying that the system of linear equations with the matrix notation becomes very simple. It looks this kind of a nice thing, very compact kind of thing. All the data is available. These are the coefficients A11, A12, A1n. These are the coefficients for the first equation, A11 coefficient of x1, A12 coefficient of x2, A1n is coefficient of xn. So the first equation is a11 x1 plus a12 x2 plus a1 xn is equal to b1, and similarly the all other equations. Okay. Now, so this is one reason. Yes, I fully agree. It makes the whole thing look very neat and clean. I don't have to write x1, x2, xn. Any other reason for that? I'm waiting for some more remarks to come.
So someone, Geeta Chaudhary on YouTube has answered that one reason can be that it is easier to write only coefficients again and again than writing whole equations again and again.
Okay, good. That is, I fully agree with that. It reduces work of unnecessarily writing something which is not required. The variables x1 to xn, they are not required, provided we keep track of what we are doing. That this one, the first column are the coefficients of respective equations for x1. This one, coefficients of respective for x2, and so on. So keep track of that.
Now there is one more interesting answer. Share it.
Yeah.
So Vijay Kumar Solanki has said when number of equations are more, then it is not possible to solve it manually. So to enter data in computer, we need some structure which is matrix.
Oh, great. So there is somebody technology oriented. Very good answer. And so what he is saying is solving 3 by 3, 4 by 3, 4 by 5 kind of equations is okay. Manually you can do it. Maybe 10 equations in 15 variables, you can do it by help of a calculator and so on. But you'll be surprised the number of equations that come across in real life problems in economics, in differential equations, in weather forecasting, in global positioning systems. The number of variables involved are very, very large. You might have heard about the name of John Galbraith, who got Nobel Prize in economics, and he used a system of linear equations which involved probably around 1,000 variables and how many, I don't know. So the point is, nobody solves systems of linear equations or analyze system of linear equations, whether it has a solution or not, manually. It is only to understand the process we give these simple examples. Otherwise, this is done by machine. So, saying that I can store this data of m linear equations in n variables on a computer means what? So that is the first thing. And how does computer solves it? How does computer analyze it? After all, a computer is a machine which is programmed to do something, and it can store data in the form of a binary system. Right? So we can store the numbers of any length on the computer. Okay. So, for example, if it is n numbers, so we'll store A11 and have some indicator saying the next one, the length of digits is coming for A12 and so on. So, all these numbers can be stored. Okay? And it can be programmed to do matrix multiplication. It can be programmed, there could be algorithms doing matrix multiplication, matrix addition, scalar multiplication, inversion, and so on. But all of them eventually boil down to the 4 operations of addition, multiplication, and so on. So the idea is, because those variables are not going to be important and we are going to deal with only these m times and numbers, they can be fed to a computer and a computer can help us in manipulating and doing these things. So the idea is, what we want to do is, given this matrix, the row echelon form says I should reduce my matrix to something called a row echelon form. So I'm going to describe what is called row equivalent form for a matrix, which is going to be the important thing for many of the topics that we are going to come across later on. So let us try to understand. We are given a matrix M, which is M cross N, M rows and N columns. So let us assume it is a non-zero matrix. Okay, because if it is zero, that is Can you please keep your mic muted so that we are able to go ahead with our interactions? Right. So M is is a matrix whose entries we can write down. We say this matrix is the M cross N matrix. We say it is in row equivalent form. It is in row equivalent form if, first of all, there is a number R which lies between, which is bigger than or equal to 1, and which is the minimum of M and N. What is M? M is the number of rows, N is the number of columns. So this R is a number, okay, which is between 1 and R is an integer between 1 and okay. Now this, once we have got an R, the second thing says that there are positive integers P1, P2, PR. Okay. So there is a number R which is between the number of minimum of the number of rows and columns, and with this index R there are positive integers P1, P2, PR with the following properties. What are the properties? The matrix M takes the form, this is the first row of the matrix R1, second row R2, third row R3, and so on. So there are possibly R non-zero rows for the matrix M, and the bottom N minus R rows are all 0. So matrix has the following form. There is a number R. So this is the number R we have said exists, and that number R is reflected here in the structure of M. The first R rows probably are non-zero. I'm saying probably. We'll describe them soon. But the bottom R N minus R rows, okay, M is the number of rows, N is the number of columns. So M is rows and columns. So M minus R, the bottom M minus R are all 0. So that is the first property. So what is the second property? The second property says, look at the row. So first we said, look at the M. M looks like there are R rows. We'll describe these rows now, and bottom are 0. And look at the top rows. So look at the ith row. In the ith row, the entries before the pith one, there were numbers I1, P1, P2, PR. So look at the number PI. What is the property of that number PI? PI is the column number. PI, AI, PI. In the ith row, pth column, AIP entry is non-zero. So this is the first non-zero entry in that row, right? All the entries before that are 0, and we don't bother what are the remaining entries. Okay, and these numbers P1, P2, PR should have the property P1 is strictly less than P2 is less than PR. So what does the matrix look like for the row equivalent form? The matrix looks like it looks like the following. There is a first row. Okay, this is the first row. The first row has got a non-zero entry, and that is in the P1 column. So this column is P1. So the first non-zero entry is for the row 1 is at the place P1. So that means all entries on the left of that is equal to 0, and all the remaining entries we don't bother what are they. They could be anything. We don't bother about that. Only the first non-zero entry should be at the column P1. For the second row, look at the first non-zero entry that is going to be at a place. Column number is P2. So we want it should be on the right side of the first one, P1. P2 should be bigger than P1. There may be in zeros in between, we don't bother about it. So column number P1, which is the first non-zero entry for the row 1, is strictly less than the first non-zero entry for the row 2, which is at column P2, and so on. And the first non-zero entry at the rth row is AR-PR, so that is will be at some place here PR. So PR is bigger than PR minus 1, is bigger than, strictly bigger than P2, is bigger than P1, which is bigger than or equal to 1. So these are the non-zero entries, they come in this fashion, and all entries on the left and below are all 0. So
There's a question. A student is asking that the first entry, that is A11, should be non-zero, I think. Can you clarify that doubt?
okay, so we are not bothered about whether that entry should be 0 or not 0, right? If you are looking at the in the row equivalent form, here. So the matrix is in row equivalent form, right? That means what? That means two things. One, that there is a number R such that the top R rows are non-zero. So what does a row non-zero mean? There is at least one non-zero entry in that row. So R1 will have a non-zero entry, R2 will have a non-zero entry, and the row R will have a non-zero entry. Okay. The bottom rows will be all 0. Okay. Now we are going to describe this R non-zero rows. In the R non-zero rows, how do they appear? In the row 1 should have a non-zero entry somewhere, right? So that non-zero entry, where it will be? It will be at some place for the first one. I'm not using the whiteboard, otherwise I could have written something. Probably next time I'll do it on my laptop. Write down something. So in the matrix, the first non-zero entry in the first row. So let us go back. In this first row R1, there is a non-zero entry somewhere. So look at, go horizontally, where did the non-zero entry come? It will come at a place, column number P1. For the R2, the non-zero entry will come at a place called P2. Okay, the first non-zero entry. And similarly for RR, because it is a non-zero row, so non-zero entry will come at a place PR. So these positions where the first non-zero entry P1 in R1, P2 in R2, PR in RR occur, they have this relation that P1 is less than P2 is less than PR, and P1 is bigger than or equal to 1. We are not saying that the P1 should be equal to 1. There is no condition on that P1 should be equal to 1. It can be, okay. So I hope I have clarified that student's remark or student's question.
Yes, she's saying she got it. Thank
Okay,
you.
fine. Right. We are not saying it could be 0, but the row Ri should have a non-zero entry. And the first non-zero entry, if it is at a pth place for the ith row, I between 1 and R, then this should happen. Okay, probably I think, so this is what the matrix will look like in a row equivalent form. I'm saying a row equivalent form because this number can be changed to make it a row. For example, this row, I can multiply by some constant non-zero number, and that also will be having the same properties. Okay, so the row equivalent form is characterized by two things. One, the number R, which is the minimum of M and N, the minimum. Okay, Why it is the minimum? Because this R is the number of non-zero rows, right? So it has to be smaller than or equal to the number of rows. R has to be smaller than or equal to, because total number of rows is M. And the second property says that the non-zero entry is coming at a place Pi. So the Pi, P1, P2, PR. So how many non-zero entries are coming at P1th column, P2th column, PRth column? So total number of columns cannot be more than N. So so R has to be less than or equal to N also. So these two things characterize a row echelon form, and probably I think time has come to do some examples. So which one of so this is audience, write down in your chat box which of these is in row echelon form. So Dilpreet, work for you.
They're saying that all are in row echelon form. All. The answer is all by 3-4 people.
Okay. Keep in mind that the zero matrix we are not really interested in. So you can say that this is in row echelon form, but we are not really bothered about matrix with all entries 0. We defined a row echelon form of a matrix only when the matrix was non-zero. I purposefully added the word non-zero here. So you can say by that definition this is not, but all remaining are in row echelon form. Now let us look at this some more to understand what we are saying.
Uh, 1 and 2 is reply.
So this one meaning all entries 0, and the second matrix probably they are counting it row wise, okay, because of row and columns. So the second example probably 0, 1, 2, 1, 0, 2. So somebody is saying that these two matrices are not in row echelon form. What about the others?
They're saying, some are saying that no matrix is in row echelon form.
Oh, great. No matrix is in row echelon form. Okay, can you pick up one of the persons and have a, I would like to have a talk with him or her.
So there is a Arup that is saying that no matrix is in row echelon form. Khyati Sharma, Shani, Devanshu Biswas. You can pick anyone.
So you are the moderator. You pick up anyone and say that you would like Professor Rana would like to interact. So let us say who is saying that this matrix is.
Arup, are you interested in Arup?
Yes, ma'am.
Yeah,
Hello.
yeah. I would
Can you
like you
please
to
answer?
why do you think this matrix which I have highlighted?
Sir, in second row, the first element, that 1 in place of 1, it should be 0.
Why?
Because the non-zero element, that means in above is 2, though below that 2, all the elements should be 0.
Good. So keep in mind, if this matrix is in the row echelon form, then look at the first row. First non-zero entry is coming at the place 2, which is column number 1. Good. Now let us look at the second row. That row also has a non-zero entry. Actually, all the entries are non-zero, and that entry is also coming at the place P1. So P2 is same as P1, which is not possible with the row echelon form. So this matrix is not in the row echelon form. Good. Somebody else would like to say? Discuss some other example?
Shivani, do you want to discuss?
So the last one is in row echelon form.
Devanshu, can you please discuss with sir?
Yes, ma'am. In this last example, in the third row, the second element should be 0.
I'm
For
not, we can't change the matrix at present. What we're asking is an objective type question, whether this matrix is in the row echelon form or not. If
no,
yes, it is not. Why not?
no, yes. So this matrix is not in row echelon form. If this that second element in the third row is 0, then it could be in row echelon form.
Yeah, so at present it is not, because
Yes.
the first non-zero entry in the last row, R3, is coming at the place second column, and in this row 2 also it is coming at the second column.
Yes.
So P2 is same as equal to P3. So that is not true for a row echelon form. So this is also not in the row echelon form. Right? So
Yes.
is still somebody having a doubt about what is row echelon form? Anybody has a doubt, please ask. We can do some more examples.
Sir, tell about zero matrix, how it is. First one.
The first one, I said about the matrix which is identically 0, right? We did not define row echelon form for a 0 matrix. We didn't say anything because we want to talk about non-zero things. So you can say this matrix by our definition is not in row echelon form because we are not looking at, we are looking at only non-zero matrices. Okay. So row echelon form is defined only for a matrix if it has at least one. For example, if I take this matrix as the coefficient matrix of a linear equation, okay, what will be the data you are giving me? Everything it will be 0, right, on the left hand side. So there is nothing much to do about the 0 matrix other than they play an important role somewhere else. So we'll talk about it when they come. So for row echelon form is defined only for matrices which are non-zero. Okay, all right. Okay. This is again something. I think we'll not do many more example other than this one now. So let us finish off this. Probably this should have been a part of. Probably shall I leave it for the tutorial? Dilpreet?
Yes, sir, you can leave for tutorial.
Okay, so I can leave this. This will be discussed. So please note it down or look at the recording later on to discuss this problem in the. I just because I wanted to do some problems so that the notion of row echelon form is clear. So here is a theorem which says every non-zero matrix can be reduced to a row echelon form using elementary row operations. So what we want to do, we want to prove mathematically a theorem saying that you give me a non-zero matrix, okay, this shouldn't be n cross n, I think there is a typo here. Every m cross n, you can have m rows and n columns. So that is not, this is a typo. So every m cross n, the matrix need not be a square matrix, it could be a rectangular matrix. Every matrix, if it is a non-zero matrix, that means it has at least one non-zero entry. It can be reduced to row echelon form. So here is a poll. How many believe yes, it is possible? How many believe it is, because I have written it as a theorem, that shouldn't mean that it is a true theorem, right?
Yeah,
So,
everyone is saying
yes, because if I have written it as a theorem, it should be true, right? So let us see, how does one go about proving it? How would you like think I should prove such a theorem? That I want to say that every matrix can be reduced to row echelon form. That means what? I'm given a matrix with entries. I think I made a mistake of not using my laptop. I'm on a desktop actually. I can't use the whiteboard, so let me probably pick up an example which is oh, sorry, no, this is not what I want to do. Okay, let me just go back and okay. So here is, so for the time being, ignore the left hand side, ignore this part. Just look at the matrix, ignore this part. Look at the matrix M cross N, which has got entries A11, A12, A1N. So that is the first row, this is the second row, and this is the mth row. Okay, so it is a M cross N matrix, a rectangular matrix, and I want to make you believe that this matrix can be brought to row echelon form. Okay, so the method is as follows. Okay, how do I do it? See, let us look at the first row. Okay, in the first row, probably the entry A11 is 0. It is possible, right? It is possible that either the A11 entry is 0 or it is non-zero. If it is 0, forget about this row. Come to the second row. Look at the first entry in the second row, A21. That may be 0, that may be non-zero. If it is 0, forget about it and come to the, go on doing this and look at the last entry, M1. So that is the first entry of the mth row, right? That also possibly can be 0. So all this possibly the entries can be, hello? All these entries, all these, does anybody have a question or?
Professor, you continue. I think already unmuted by mistake.
Okay, okay, no problem. So look at the first column of this matrix. The first column either has a non-zero entry somewhere or all the entries are 0, right? If it has a non-zero entry somewhere, A11 may be 0, A21 may be 0. Say, let us say A31 is not 0. Then what I will do, I will interchange the third with the first row. I will interchange that. So what will the result be? When I interchange the row, third one, it is a non-zero entry here, A31, that has become a non-zero entry in the first place. Okay. So if in this column, anywhere a non-zero entry is coming, interchange that particular row with the first one, so that the first entry here is non-zero. Is the first step clear to everybody? I am looking at the column of the matrix. Scan the column of the matrix, first column of the matrix, and spot if there is a non-zero entry coming in the first column somewhere. If at any place it comes, if it comes at some particular row, make that row as the first one and interchange that. Okay. So your first row will have a non-zero entry at the first place in case there is a non-zero entry at all in the first column. So that is the one case. The second case is all the entries are 0 here. All the entries are 0 here. Then forget the first column, go to the second column. Go to the second column. Look at the second column. In the second column, look at the entry A12, A22 and so on. Either there is a non-zero entry somewhere sitting. Interchange that row with that particular row, first one. Right? If all are 0, forget about that. Okay. So what has happened in the process? Either this is all 0 or this entry has become non-zero. Or if all are 0, then again in this place either we have made this entry as non-zero or everything else is 0. And I can continue this process. So what will happen? Even at the second stage, once I made this entry as non-zero, If I forget this and forget this, I've got a matrix of smaller order, right? I can continue this process. So by this process, I can bring the matrix as soon as all the scanning of all the columns is over. You have to find a place where a non-zero entry is coming because the matrix is non-zero. So there will be a place somewhere in this scanning of columns, scanning column 1, column 2, column n, some non-zero entry comes somewhere, make that as the first row and interchange and go on doing that. So that will make the whole matrix in row echelon form. So that is the process of making a matrix in the row echelon form, and that you can write mathematically as induction that either the first row is non-zero, somewhere there is a non-zero entry, make that entry as non-zero. All remaining entries you can make it 1, make them 0 by adding and subtracting. Right? If this entry is non-zero, then all the bottom entries can be made 0 by multiplying suitable constant and subtracting. All this can be made 0. So as a first step, you can make this entry as non-zero and everything else below that to be 0. And now forget this row, forget this column, and the remaining by induction you can go on doing it. Okay. So that is a systematic process of reducing a matrix to row echelon form. Now anybody has a doubt to ask, please ask. Is the process clear? This is a systematic process.
Yes, everyone is saying it is clear to them.
Because we can tell computer to do this process. Once the data is in the computer for the matrix, we can tell the computer, please scan column 1. If all entries are 0, forget it, go to column 2. If all entries are 0, go to column 3 and go on doing it till you have reached the last column. Because there is a non-zero matrix, so a non-zero entry has to appear somewhere. And at any stage where a non-zero entry appears, interchange that particular row with the first row so that that entry becomes non-zero. On the left, everything is 0, and you can make everything below that also equal to 0. So this process, because there are only finite number of columns scanning, so this process has to end. And you can write it mathematically, proof by induction, that every matrix has got a row echelon form. So is everybody clear about row echelon form? Because I think it's time. We have to stop at 7.
Yes, sir.
Okay. So if I think tomorrow I'll be slightly better organized with my laptop, I can write something, because today I thought everything on desktop, that is not a good idea in a mathematics lecture. I never do that. So one has to learn. There is a whiteboard in this WebEx where one can write something.
Check this option and inform you.
Yeah, just check. I think there is in Google Meet and
in other platforms,
it's there. But anyway, I'll probably bring my own whiteboard to write something next time. Okay. So today what we have learned is linear algebra arises because of linearity, and linearity or geometry in the algebraic setup. Okay. So you can see now from linear equations we are entering into algebra, and so that is the one reason what is linear algebra, and linear algebra finds applications everywhere that you will see by the end of the course. A lot of applications of linear algebra. So what we have done is studying linear equations lead to something called row echelon form of a matrix, and we'll see a lot of applications of row echelon form in the time to come. And the reason for that is because row echelon form consists of only numbers, and so it gives rise to a matrix, and matrix operations can be done by a machine to save time. So let us stop that. So bell goes on saying that it is time to stop. Is that the bell to stop, or somebody is?
I don't know how it is ringing. Okay.
Okay.
So,
Fine.
Okay. Thank you. Thank you very much for wonderful talk.
So we'll meet tomorrow at 5:30.
Yes. So I would announce to all the participants that we will be meeting tomorrow at 5:30 p.m. Professor Rana will continue this discussion, and I will send you link for WebEx as well as YouTube Live today, most probably by tonight. Okay,
And
please check your email.
so here is a
Yep.
request that please go through this concept tonight if possible, and keep and tomorrow morning, and keep your questions about it ready tomorrow in case anything. We'll start with your questions and then go over to other things.
So recording is available on YouTube. So if you want to watch this lecture again, you can watch it again.
Okay.
Okay.
Right.
Okay.
Thank you.
Professor Rana, shall we end it here?
Yeah, please go ahead.
Okay. Thanks you everyone. Bye. See you tomorrow. I'm ending the meeting for all. Bye.
Yeah, please.